Hi, my name is Nimrod, and today I'll talk about my work with Professor Nimrod on efficient distance estimation for dense graph properties. We start by introducing property testing and distance estimation and how they are defined in the dense graph model. As this is online, if you are confident that you understand all three terms, feel free to jump ahead. We look at some previous work to provide context for results, go over our list of results, review our framework, and give an example for how we prove one of the results induced before freeness using the framework. Finally, we'll discuss some open problems and approaches for solving them. Let's begin. A property is a defined subset of objects that belong to a model which has some distance metrics. A property testing algorithm for property P is given an input object and an error parameter epsilon. It samples part of the input object and guesses with some constant probability whether it belongs to P, the yellow section in the drawing, or is far from P, the blue section. The algorithm may return arbitrary results if given an object not in P, but in distance less than epsilon from it, the green section. Different models are made for different objects, properties, query types, and distance matrices. The questions in property testing are to understand for different properties what is the query complexities of their testing algorithms as functions dependent on the size of the input object and on the error parameter epsilon. A property is testable if it has a property testing algorithm with query complexity that only depends on epsilon. One-sided testing algorithms are ones that have only false positives. That is to say, if an object belongs to a property, the algorithm must say it belongs to it. If it does not, the algorithm is allowed to err in some probability. In distance estimation, as the name suggests, the goal is to tell how far an object is from a property. A distance estimation algorithm for property P may be given an error parameter epsilon and an object G. It should return with high probability an estimate for the distance between G and P. As you can check for yourself, distance estimation algorithm can be used as a black box for two-sided property testing. Our talk is about the dense graph model. As its name suggests, the objects studied in the model are undirected dense graphs. By dense, we mean theta of n squared edges. The queries in this model are vertex pair queries. A single query asks if a pair of vertices uv are adjacent. The distance between two n-vertex graphs is defined as the symmetric difference between the edge sets of the two graphs, normalized by n squared. This also means that the distance between any two graphs that are not dense is basically zero, as they are both close to the empty graph. The distance between a graph G and the property P is the distance between G and the graph closest to it that belongs to P. Now let's discuss previous work. We'll go over a small number of previous results in the dense graph model, moving between testing and distance estimation, starting from more general results to more exact. Note that many important works are not mentioned here, and a more complete survey exists in the paper introduction. Most generally are the results of Alon and Shapira, give a combinatorial characterization for which properties are testable in the dense graph model, and the ones of Fisher and Newman, which shows that this is also the set of properties that are estimatable. The results of Fisher and Newman set the dense graph model apart from models such as the bounded degree graph model and the Boolean function model, in both of which there are properties which are testable but not estimatable. The above two results characterize which properties have complexities dependent only on epsilon. However, the dependency shown is very high, more than a tau and 1 over epsilon. They leave room for the characterization of which properties have equivalent testing complexities with a lower dependence on epsilon. Specifically, progress has been made to give a partial characterization for which properties have testing dependence that is polynomial in epsilon. These properties are called easily testable, rather than thus testable. Goldreich, Goldwasser, and Rom show that properties called partition properties are polytestable. For a subset of these, they also show polyestimation. Implicit in more recent work and clarified in our paper, it is shown that all partition properties are in fact polyestimatable. A type of graph properties that have been studied in the context of property testing in different models are those defined by being induced subgraph free for some small fixed graph. For instance, the property of having no induced triangles, or the property of having no induced cycles of size 5. Alon and Shapira show a lower bound for induced H freeness for any H other than a cycle of size 4, a path with 4 vertices, a path with 3 vertices, and a single edge, or a path of size 2, or the complement of one of these. The lower bound they show is that of inverse epsilon powered by log of inverse epsilon. As this is higher than a polynomial in 1 over epsilon, these properties were shown not to be polytestable and thus also not to be polyestimatable. Nearly all induced H-free properties not covered by the above lower bound, which is a finite number, are shown to be polytestable. P2 freeness is trivially testable and estimatable. Induced P3 and P4 freeness were shown to be polytestable. Induced C4 freeness was shown to be testable in equal complexity exponential in epsilon, which is a large improvement on the former higher bound of a tower of log 1 over epsilon. The question of whether it is polytestable is still open. Finally, caudality, the property of having no induced cycle of size bigger than 3, was recently shown to be also polytestable. A few other results exist for polytestability, but none for this estimation. Our work closes some of this gap by giving estimability results that match the mentioned testability ones. As mentioned in the previous slide, our work presents estimability results to match the aforementioned testability ones. We show induced P3 freeness and induced P4 freeness, as well as caudality, are easily estimatable, and show that C4 freeness has an estimation complexity that is at most exponential in epsilon. We'll proceed to discuss our framework. Our framework leverages just one distance estimation algorithm to achieve all of the above mentioned results. It does so by using property covers. A family of properties F, epsilon covers some property P, if any graph that belongs to the union of F is epsilon close to P, and any graph that belongs to P is epsilon close to some property in F, as can be shown in the drawing. As shown in the drawing, the graph is of distance delta to property P, if and only if it is a distance delta plus minus epsilon over 2 of the property closest to it in F. Therefore, if we have distances from G to all properties in F, we could calculate the distance from G to P. This is formalized in lemma 1. Note the logarithmic dependency on the size of the cover in the lemma. The dependency is not linear because the distance estimation algorithms for the different properties in F can reuse the same queries. The logarithmic dependency comes from Chebyshev's inequality, because if we want to be confident we have the correct result for the distances from G to all properties in F, each distant estimate must be correct with probability O of 1 over the size of F. A corollary to the lemma is that if a property P has a small enough cover for very efficiently estimatable properties, the lemma shows P also has an efficient distance estimation algorithm. Note that a similar lemma to lemma 1 exists for testing. As I said, our framework uses just one distance estimation algorithm. It is for semi-homogeneous partition properties. These are the building blocks for our covers. A semi-homogeneous constraint on a cut between two sets of vertices is one of three constraints: that the cut is complete, that the cut is empty, or the don't care constraint, that the cut can have any set of edges. So only one of these three constraints is a semi-homogeneous constraint. We will make a slight use of the notion of cuts. We also talk of cuts between a set of vertices and itself, in which case a complete cut means the set of vertices is a clique, and an empty cut means it is an independent set. A k-part semi-homogeneous function is defined on the set of unordered pairs of k parts, v1 to vk. It maps each pair of parts to a semi-homogeneous constraint on a cut, complete, empty, or don't care. Each such function defines a k-part semi-homogeneous partition property, or SHPP for short. A graph belongs to an SHPP if its vertices can be partitioned into k parts, so that the cut between the part I and part J follows the constraint specified for this pair of parts in the semi-homogeneous function. Let us follow this example, which look at the constraints on part P1 of some semi-homogeneous partition function. The function maps P1, P1 to the complete constraint. So all vertices assigned to in G assigned to P1 must form a clique. The function also maps P1, P4 to the complete constraint. So the cut between vertices assigned to P1 and vertices assigned to P4 must be complete. P1, P3 is mapped to the empty constraint, and therefore there must not be an edge in G between vertices mapped to P1 and vertices mapped to P3. While P1, P2 is mapped to the don't care constraint, so any mapping of vertices will follow this constraint. Okay, so if there exists a mapping between the vertices of G, any mapping to parts, to k parts, so that the cuts between the parts follow the semi-homogeneous function, then G belongs to the semi-homogeneous partition property. Distance to a k-part SHPP can be estimated by querying an induced subgraph of size polynomial in 1 over epsilon and log k. Let P be a property that is coverable by a family F of SHPPs, each with at most k parts. Then P has a distance estimation algorithm with query complexity polynomial in log f, 1 over epsilon, and log k, as a corollary of the above two lemmas. Our results are hence focused on showing that each property from our results section has a cover F of k-part semi-homogeneous partition properties, such that k and the size of F are both at most exponential in epsilon. Considering the global structure of semi-homogeneous partition properties, in contrast to the local definitions of induced H freeness, I think that these results are interesting in a combinatorial sense, even without the implications on distance estimation. And maybe they have more uses. Next, we'll show how our framework can be used to prove induced P3 freeness is easily estimatable. Recall that a P3 graph is a path with 3 vertices. We will use the following known characterization of induced P3 free graphs. A graph is induced P3 free if and only if it can be partitioned into disjoint maximal cliques, such that each vertex in the graph belongs to exactly one such maximal clique. In the drawing, you can see that indeed a vertex that belongs to more than one maximal clique will be at the center of an induced P3. How does this relate to a cover by homogeneous partition properties? First, note that the property of having k cliques is in fact a k-part HPP. This is just a property where the constraint between each part and itself is 1, and between each part to other parts is 0. This is not enough to use the corollary from our framework, because some graphs will have a very large number of maximum cliques, even one that is dependent on n rather than epsilon. For example, the empty graph, which is also induced P3, has n maximal cliques. We show, however, that the HPP of having 2 over epsilon independent cliques is in fact a valid cover. We do so by showing that any induced P3 free graph can be modified with at most epsilon over 2 n squared edge modifications, so that it will have at most 2 over epsilon maximal cliques. We do so by greedily merging cliques as long as possible to merge cliques that result in a clique of size at most epsilon n over 2. The modifications create at most 2 over epsilon cliques, as in the case of running this algorithm on the empty graph, and creating each clique adds at most epsilon n squared over 4 new edges to the graph, as can be seen in the computation below. So overall, the new graph, which belongs to our cover as it has just 2 over epsilon cliques, is at distance epsilon n squared over 2 from the original P3 graph, as required by definition of a cover. So indeed, this property alone covers induced P3 free graphs. It is not obviously identical to this property, as the empty graph is induced P3 free, but does not belong to the property, but it covers it. And the empty graph is close to this property. As we've now shown that this is a cover for our property, we can proceed with the corollary. Our family is just one property with O of 1 over epsilon parts. Just to complete the proof. Finally, we discuss some open questions. The first question is pretty straightforward. It asks whether there are properties which have testing complexities that are considerably more efficient than their estimation complexities, or are the complexities similar for all properties in the dense graph model. Our work, as well as that of others, suggests the latter. Interesting other results to read in regard to this question are, of course, the one of Fisher and Newman, which shows that all testable properties are also estimatable, and the more recent result by Hoppen et al., which uses the weak regularity lemma to show a connection between parameters of the removal lemma for hereditary properties, which is used to show efficient one-sided testing, and estimatable complexity. This first question is probably pretty hard, and I would start solving it with questions 2 and 3. Question 2 asks how can we extend the SHPPs in ways that can show more distance estimation or property testing algorithms. Gishborn and Shapira show that induced C4 freeness cannot be covered by homogeneous partition properties of size that does not depend on epsilon n. However, as we've shown in our work, with semi-homogeneous partition properties, you can cover induced C4 freeness. So this addition of semi-homogeneous constraints is what allowed us to achieve this result. Perhaps by finding different property covers, even if some of them will be less efficient than the ones for SHPPs, we can result in better bounds on distance estimation and property testing. Question 3 goes in the other direction and asks, which are the properties that can be covered by SHPPs? That is to say, with a cover of complexity that is only dependent on epsilon, because all properties are actually covered by SHPPs if you allow them to be of size exponential in n. I think this question can be quite interesting combinatorically, even without no results for property testing and distance estimation, because of the structure of the semi-homogeneous partition properties. My guess is that the answer for question 3 is the set of hereditary properties, that is, the properties that are testable with one-sided error. Note that this does not say that all these properties have distance estimation in the same complexity as testing, because even if a cover exists, it can still be large. Also for properties that have comparably small testing complexity. So an interesting follow-up question for question 3 is for which properties a cover by SHPPs hold their true testing and estimation complexities. That is to say, for which properties covered by SHPPs, applying our corollary on a cover by the SHPPs results in the most efficient distance estimation and testing algorithms. I think that maybe solving this problem will actually be helpful for solving question 1. Thank you very much for listening, and I'm always available for follow-up questions.